Hi everybody and welcome back to Digital Integrated Circuits. I'm Dr. Adam Teman of the EnICS Labs at Bar-Ilan University, and today we'll go on to Lecture 3, which is called MOSFET Modeling. So we have 5 parts in our lecture today, and we'll start with basic MOS models. Well, before we start discussing basic MOS models, I want to discuss the difference between TCAD and compact models. So TCAD, or Technology CAD, is a simulation environment for accurately simulating device behavior. What it is basically, it's a very, very accurate simulator where we provide a process recipe and the device layout. Doing this, we can produce the IV curves or the CV curves, IV being current versus voltage, CV being capacitance versus voltage, and this is a very accurate simulator does this. It's used to predict device physics and process physics, but it's a very, very long and hard simulation. It takes something like an hour to a day for each IV curve simulation, and it takes hundreds of megabytes of RAM per transistor. So TCAD is very, very slow and memory hungry, and therefore cannot be used for circuit simulation. What we do instead is we use what we call a compact model. A compact model, also known as a SPICE model, or sometimes we could call it an ECAD for electronic CAD model, are simplified models that are used for circuit simulation. Everything that we've done probably in previous courses until now is a type of a compact model. What it is, it's a set of equations that SPICE or a similar simulator like Spectre can use to calculate IV or CV curves. It should be fast. It should take less than 100 microseconds to produce one IV curve, and it should take less than a few kilobytes of memory per transistor. While TCAD is used originally to produce basic compact models, once we have actual data from manufacturing, we usually take it and when we extract the actual coefficients for these equations that we have in these compact models from measurements. So we take the measurements, we take something like MATLAB or some other tool and do fitting to make to find out what the actual coefficients should be. So SPICE and other simulators use compact models for calculating device behavior, and this can be done on hundreds, thousands, and maybe even more than that devices. It's not what we use for things such as logic simulation or gate level simulation, which SPICE is way too slow for, and we can discuss that in other courses such as the digital VLSI design course that you can find links on my YouTube page. So in this lecture, I'm going to go through several of these models, and we always are going to trade off this speed or simplicity versus accuracy. And you can see down below here all of the different models that we're going to overview in this lecture. And we'll start with the basic and most simple one. And the simple one is called the switch model. And actually, what we're trying to do when we're building a transistor, or at least a MOSFET, and the same could be said for like a BJT transistor or even other types of switches, is that we want it to be a real perfect switch. So what we want is this thing. Okay, so we want our transistor to be a switch, and of course the switch can't be completely ideal, so it has to have some sort of an on resistance. So this is what we would want. That we have a source, a drain, and a gate. That's what we have in our MOSFET, right? We have our gate, we have our source, and we have our drain. And we have the different voltages between them, such as VGS, and maybe I guess we could say VGD, which we don't really use, and VDS. And what we want to show is some sort of a relationship that will give us an IV curve between them. So first we say that, look, we have this threshold voltage that's called VT. If we take VGS and we bring it above VT, then this switch closes, so we have a short circuit here, right? So we do this once VGS goes over VT. Once it does, we have a current that goes between the source and the drain, and it goes over this on resistance. So our current then goes between the drain and the source with this on resistance. That's the type of model you'd want to do. If I draw the IV curves for this, first of all, I look at a model for VGS versus IDS. So taking VGS as our parameter that we're going to change, we're going to raise VGS. Starting from 0, we're going to have no current, and once it passes this magical threshold voltage, we're going to be able to support any current that should run on IDS. So it's like a nice step function type of a thing. Okay. Thereafter, we have to look at VDS. So we have VDS is the voltage that's falling over the resistor, and since we have some sort of on resistance, the IDS, the current that's going through the resistor, that's IDS, and that's VDS. The current going through the resistor has a constant slope, which is 1 divided by R on. So the switch model gives us this pair of ID curves. One is VGS to IDS, and the other one is VDS to IDS. And this is the type of model that we'd want to use. It really helps us to build a gate, like, I don't know, if we'd want, say, a NAND gate or something like that, we can easily build it with such a switch model if we're able to build it. And that's what we want our transistors to look like. Unfortunately, this is very inaccurate. So let's start making it kind of a bit more accurate, trading off the complexity of the model, what we can do with hand calculations or even maybe in our head, to what we can do with a computer, and maybe we can't even do with a computer because it's too it becomes very complex, such as those TCAD models that we said is only 1 or 2 devices or so. So our next step would be a piecewise linear model. So piecewise linear models are types of models that are used often when we want to simplify things that are not linear, and they're not that nice, but it makes it much easier for hand analysis. Okay, so we have to take the fact that in our switch model, we could have raised VDS arbitrarily and gotten a higher and higher current. And we know that that's not true. In fact, once our channel reaches what we call pinch off, we get a saturation of the current. So let's put that into our model, and we can do this piecewise linear part. So as long as our current is rising up to this, again, a magical parameter, which is VGT or VGS minus VT, as long as we get to that, we're rising with this 1 over R on type of a constant slope. But once we reach that, our channel pinches off, we saturate, we can't do anything more, and our current stays constant at what we call IDSAT, a saturation current. So if we want to use a bit better model that actually kind of looks like what a transistor is running for a VDS to IDS curve, we can use this piecewise linear model. But again, this isn't very accurate. Okay, one of the reasons is we have channel length modulation. We saw that actually our output resistance is finite, it's not infinite. That's especially important for analog circuits and analog simulations, but also we know that there is a dependence of the current on VDS even after we get to our pinch off. So that we call channel length modulation. The more we raise VDS, the shorter the channel becomes, and then the VDS voltage falls on a shorter length and gives us more current. Okay, so how we can do that is we can take, again, a piecewise linear model, take our regular 1 divided by R on slope here, and then once we get to pinch off, instead of having this 0 slope, we can have a slope that is equal to lambda IDSAT, where lambda is the channel length modulation coefficient, and actually this is similar to what we had in BJT circuits, where it crossed the x-axis at a voltage that we called the early voltage. So it's sometimes called the early effect, even though early is something that was for BJT transistors, and this is channel length modulation. If we want the scheme of this type of a piecewise linear model, what we have here is we have our IDSAT over here that actually has this resistor that's 1 over lambda IDSAT in parallel to it, and then when we put VDS over it, our IDS current actually is both the IDSAT plus this extra this extra part, which is raising our total voltage through the transistor. But we want something better, and that brings us to the Shockley or square law model, which is probably the most famous MOS model of all, and especially in analog circuits, we try to reach this in order to make easy-ish hand analysis. This is also called a long channel transistor model. So this is a bit more accurate, and we actually base it on physics to develop it a bit more than at least what we were doing with our previous piecewise linear models. So if we have the current through a transistor at some point x along the channel, we know it's just the speed of the electrons, that's ni over here, times the charge at that position x along the channel. We also have some sort of width of how many electrons are running along the channel at once. This would be the W of the transistor. So we multiply that by W, and the amount of charge that's running through in an infinitesimal type of a length, which we call dx. So our total current is ni times q at point x times W dx. Now we have to find out what this ni is and what this q is. So if we look at q of x, that's the charge at some point x along the channel. And if we look at our channel, so we have our substrate over here with our, say, our n plus diffusion and our n plus diffusion, and this we called the S and this we called the D, and on top of that we had our gate. And we know that we need to lose over here Vt to, that's in order to cause a channel. Okay, but then we have some sort of Vc of x at this point. Actually, at every point x along the channel, we have this Vc of x. Here we have this Vgs. Here we have this Vt, right? And here we have this Vcs of x. Okay, so that means that the actual voltage that's falling over this area x is just Vgs minus Vc of x minus Vt. And we know that the charge is just C times V, or the capacitance times the voltage, and the capacitance is C aux, which we remember is epsilon aux over T aux, okay, which is the capacitance of the gate. And we can also look at the ni over here, which is the again the velocity or the speed of the electrons. So the velocity is just the mobility of the electrons times the electric field at that point. And the electric field at any certain point is the change in voltage over that length. So it's dV to dx. So we can say it's the mobility of electrons times the difference of the voltage over that point. So now we have an entire formula for ID. So ID equals this times this, right? And we what we can do is we can then write that down. So ID of dx equals mu n C aux w Vgs minus V minus Vt times dV. And then we can just integrate that. So as we saw before, we had our MOS over here, and this whole channel length was L, okay, and over here was D, and over here was S. So we can run from the voltage 0, which is, let's say this is connected to 0, or our reference voltage, until VDS. So we can run from 0 to VDS, and we can run from length 0 to length L, right? So we integrate from 0 to L, see what the current is at every x from 0 to L. We see what the voltage is on for the dV on every voltage from 0 to VDS, and we do that over this formula up above. And when we solve the integral, we get mu n C aux W over L VDS times VGS minus VT minus half VDS, which is our kind of known Shockley model for linear current. This we called K, or transconductance. Okay, at pinch off, that's where we saturate. Pinch off, we said, is a VGT, or VGS minus VT. We know that the voltage over the channel is constant, so we can substitute VGS minus VT for VDS inside this formula over here, and we get that the saturation voltage, which is IDS for VGS minus VT, is just this K over 2 VGS minus VT squared. And this squared over here is where we get the name square law, and we see that we get this this VGS, and this ID gives us something that is x squared, or VGS squared, right? Okay, so that's a square law model. So if we look at this, we can make it with a bit of a simpler expression. How we take this VDS and exchange it with what we call VDS effective, which is just a minimum of VGT, VGS minus VT, and VDS. So instead of what we had before, we can take one single equation, or one single formula expression, and show that this is K, right, times VGT times, instead of VDS, we put VDS effective in these two places, and then if it's VDS, then this just becomes VDS, so VGS minus VT times VDS minus VDS squared over 2, which is our just regular linear equation. If it's VGS minus VT, this becomes VGS minus VT, so this times this becomes VGT squared minus half of VGT squared, so we get K over 2 times VGT squared, which is the square law model. We also added the channel length modulation factor. So we have basically one expression that shows us the whole entire Shockley model. And if we look at this in our IV curves, we have the VGS versus IDS curve will give us this VGS squared proportion over here. And of course, it's different for different values of VDS. And if we take the VDS for IDS curve, what we have here is this type of a curvature in this linear area, and then it straightens out to this channel length modulation area after saturation after pinch off at the VGS minus VT point. This, of course, would be our saturation area, and this would be our linear area. Okay, so that's, and we call this point of VGS minus VT, we call the current there IDSAT. So that's the Shockley model, but it's also not very accurate. And why is it not very accurate? Well, when we look at the short channel device versus a long channel device, we see that over here we get this linear slope. It's not a square slope anymore. So if there's a linear dependence on VGS, I guess the Shockley model or the square law model is not correct anymore. And when we looked into that, we could see that this is due to velocity saturation. What exactly is velocity saturation? Well, here we can show the graph of we can show the graph of the field as the speed or the velocity is a proportion of the electric field, and the slope of the field is proportionate to the slope is the mobility. So this is a graph of the mobility. Okay, and what we see here is that as we go up, once we pass some point which we call the critical field, we get a saturation in the velocity. Okay, and that happens at about this NISAT. The saturated velocity is about 10 to the 5th meter to second. Okay, remember that the field is the voltage over the length. All right, so that brings us to the VSAT, or the velocity saturation model. So we want to approximate this curve, and we say that the velocity is approximately, well, we know that it's VSAT once we're over the critical field, but under that we have this curvature, which is the mobility times the field divided by 1 plus the field divided by the critical field. And that's something that we can use, but we know that at this point we have to have continuity. So if we replace the critical field at this point, we need to get a continuous model. It needs to be equal to NISAT, and that brings us to the equality that the critical field is 2 NISAT over mu, over the mobility. Okay, if we now integrate, what we're going to get is that IDS is now similar to what we had before over here on the right side, but we're going to have this kind of a new type of transconductance on the left, where we have a proportion to the L, to the length of the transistor, which we didn't used to have over here. Okay, it's kind of hard to use that, but it brings us to an important conclusion. So this was the expression that we found before, where we had this kind of ugly thing on the left side here. But we also know that for a velocity saturated device, we should have what we wrote before, the W times Cox times VGS minus VDSat minus VT, which is where we are going to be saturated at some sort of VDS, that's a saturation voltage, times NISAT, which is going to be the saturation velocity. That should be the IDS, according to what we wrote a few slides ago. Okay, so then we can equate the two sides, and we get to this type of an expression for this voltage, this VDSat, the voltage, the VDS voltage that will bring us to velocity saturation. It comes this thing where we have VGT times the critical field times L divided by VGT plus the critical field times L. Okay, and what can we do with that type of an expression? Well, we can look and see what happens if we take a few things to the extreme. So let's say that we have this E crit L, right? Or we have this critical field times L, and say it's very much bigger. It's way bigger than VGT. Okay, and when will that happen? That will happen when our L is really big. Okay, so if that's the case, then we look at the denominator here, and this is much bigger than this. That means that we can basically remove that guy, and if we remove that, then now we can take the top and mark off these two, and what we have left is VGS minus VT, or VGT. So if we take a very large L, a very large length transistor, basically VDSat, the saturation voltage, is just VGS minus VT VT, which is the pinch-off point. And that brings us back to our regular, at that point we come back to our regular Shockley model. And that's why we say for a long channel transistor, the Shockley model is what we can use. But what happens if we take the other situation where the length is really small, and then the critical field times L is much smaller than VGT? In that case, we can cross off this guy. If we cross him off, then the VGT and the VGT mark each other out, and we're left with the critical field times L, and that's the velocity saturation point. So we can say that the saturation voltage is the critical field times L. And that's the short channel transistor equation. Still, it's a bit hard, so we can make some more assumptions and simplifications and get to what we call the unified model, which we can use for hand analysis pretty easily. Okay, so instead of using the VSAT model, what we're going to do now is we're going to look at this this mobility curve, or the field to velocity, and we're going to see that it's supposed to have this curvature over here, but instead of the curvature, we'll make a piecewise linear assumption. So we'll take a linear part here, okay, where we have mu, and then over here we're just going to saturate completely, and we're going to say that to make it kind of close, instead of having here, which would have been the critical field, we're going to take it at half the critical field. It's going to so we don't miss a lot. We obviously have this part where it's not accurate, but it's not that bad, and it simplifies our model. Same type of a thing we have with the VDSAT. If we plot the VDSAT, we're going to have this, again, curvature type of a thing. So instead of that, we'll take this piecewise linear here, that at the critical field L over 2, we have the saturation of the VDSAT over here. And if we make that assumption, now we can actually bring us to the unified model. We can plug it in, and we get this very nice equation, or a nice model. So we get this K right over here, this mu n C ox W over L, times this VGT times VDS effective minus VDS effective squared over 2 times 1 plus lambda VDS, which is our channel length modulation. And we just have to write a better expression for VDS effective, where instead of just VGS and VT, now we have to take VDSAT into the equation. So it's the minimum of VGS minus VT, VDS, and VDSAT. Okay, if VDS is our minimum, then we're in linear. If VGS minus VT is our minimum, we're in saturation. And if VDSAT is, we're in velocity saturation. Okay, so that's our new type of a thing, and we just should write that the VDSAT is the critical field times L over 2, and the critical field is equal to 2 NISAT over the mobility. So those were our basic MOS models, and now let's continue to some more advanced MOS models. So one of them is called the VT star model. And what is the VT star model? Sometimes we want a real simple model, but we saw that our switch model was just too inaccurate. However, we can assume with a short channel transistor that we're always operating it at either 0 for off or VDD for 1 when it's on. And if we get VDD, we can assume that it's velocity saturated. So let's make this assumption that our transistor is either off or it's velocity saturated. And then what we can do is we can rewrite our expression for the velocity saturation a bit. So we had our IDS, and I'm just going to move things around a little bit here, equals K times VGS minus VT times VDSAT minus half VDSAT squared. Let's take our VDSAT and just bring it out of the expression here. And so we can take VDSAT out here of the parenthesis, and we get K times VGS minus VT plus VDSAT over 2 times VDSAT. Well, let's just take this factor over here, and we'll call it VT star. It's a new type of threshold voltage. Instead of just VGS minus VT, it's VGS minus VT plus a little bit VDSAT over 2. But we'll give it a name VT star. And that's real nice, because then we can come and say, okay, this is our VGS versus IDS curve. Let's say this is our new VT. We actually call it VT star, right? Anything that's under VT star, we can assume that our transistor is off. And VGS, we said, is usually going to be 0 if it's off. So we can live with the fact that we have this wrong area over here. But once the VGS is over VT, we get this linear rise. And remember that our real line is going to go like this, and it's going to be linear. So when we're at VDD somewhere over here, it's going to be pretty on the spot, and when we're at 0 over here, it's going to be pretty on the spot. So this is a real simple piecewise linear model that kind of takes into account our velocity saturated short channel transistor, and it's used in many different developments that have been shown over the years to make simplifications of all kinds of models. However, if we want a kind of more accurate model that is easy to use for a hand analysis, the popular model is called the alpha power law model. So quite a long time ago, Sakurai found that by changing the exponent of the square law, better fit can be found with simple calculations. So if we took our regular Shockley model, and this is already in the 90s sometime, we're talking about a long time ago, and we took the measured curves over here, which are these little dots that we can see over here, and we take the Shockley model, we see that there's a huge difference between them, and this is really a long time ago, and we see that there's almost no correlation between these two types of curves. And this is with L of 1 micron, so these are real old technologies. It was really bad. But what is the Shockley model? It's mu c ox W over 2L, VGS minus VT squared. Well, let's change the square into an alpha, and let's play around with this alpha, move it left and right, and see if we can move the graphs and make them fit. And wondrously, at that point, if we took alpha that was equal to 1.3, look how nicely the curves would fit onto the measurements. So that's the alpha power law model, and it has been used at many occasions to make a good estimation for what a short channel transistor is going to do. But again, this is also not accurate enough. It's nice for hand analysis, but when we have a computer and we can run heavier simulations, we want something that's very accurate. We don't want to tape out our chip for millions of dollars with non-accurate models, and that's where BSIM, or Berkeley Short Channel IGFET models, came in. So the BSIM group at Berkeley, they came up with this very, very complex model for taking into account all of the physical properties and allowing a lot of fitting parameters into a compact model that would be able to be plugged into SPICE and used for simulating a transistor. So BSIM 1 and 2 are quite old, from the early 90s. BSIM 3 is still used in technologies that are made nowadays, such as 180 nanometer or so. But basically, for the last number of years, BSIM 4 has been the de facto type of version that's been used for planar transistors. It's if you go and download the user manual, you'll see it has a few hundred pages in there with lots and lots of equations explaining exactly what all of the coefficients and how to calculate the different parameters, what an actual VT is, what actual mobility is, and so forth and so on. And you'll see that there are a lot of parameters that are just fitting parameters that are added in order to make nice fits between what we get in simulation and what our measurements are. So that's the main model for bulk CMOS, and it takes into account most of the physical effects as well as many fitting parameters. The Compact Model Coalition was started, the CMC, to actually maintain, promote, and choose new models, maybe kind of make a standardization of them. And there are many other models in different groups. Berkeley doesn't have a monopoly on this. So there's the EKV model, and there's the PSP model, and there are different models that try to show that they're better than the other ones and should become kind of the industry standard that's run in SPICE or Spectre or whichever simulator you're using. Nowadays, we can't use the standard BSIM anymore because we've gone over to non-planar transistors such as tri-state FinFET transistors, tri-gates, gate-all-arounds, and FDSOI. And so BSIM has put out this BSIM SOI, and we also have this BSIM CMG for multi-gate or tri-gate transistors, or FinFETs, whatever you want to call them. And in addition, different other models will try and take that into account. Plus, we have models for BJTs, for STT-MRAM, and other types of devices. So we're going to want to use these types of compact models with lots and lots of parameters and plug them into SPICE and use them for our simulation, and not one of the hand analysis models that I showed before. But when we do all kinds of research, often to bring some sort of a analysis, we want to use one of the more simple models and shows that it kind of correlates to what we're getting in simulation. So that was it for modeling, and now that we have that, we can go over to the next stage, which is looking back at threshold voltage and seeing what it really is after we have some models and we can take into effects that we've learned with manufacturing process.